In our human experience, we are creatures of warmth. We are drawn to the gentle heat of a campfire, the life-giving energy of the sun, the simple and profound comfort of a warm embrace. Warmth, to us, is a presence. It is the feeling of energy, of motion, of life itself. And cold, in our intuition, is the opposite. Cold is not a presence, but an absence. It is the taking away of heat, the slowing down of energy, the quiet retreat of life in the deep stillness of a winter's night. We understand this on a deep and primal level, and so it is only natural that we would ask a simple and a profound question. How far can this process go? If cold is the act of removing heat, is there a limit? Is there a point where all the heat has been removed? Is there a final, an ultimate, and an absolute cold? The answer, from the quiet and elegant world of physics, is yes. There is a fundamental floor to temperature, a bottom to the cosmic thermometer. It is a state of being known as absolute zero. But this is far more than just a very cold temperature. It is a theoretical destination, a place of almost perfect and unimaginable stillness. It is the point where the constant, vibrant, and chaotic dance of the atoms and the molecules that make up our reality is supposed to slow to a near-perfect halt. It is the place where the very concept of heat ceases to have any meaning. It is the quietest, the stillest, and the most peaceful physical state that the universe will allow. It is in a very real and a very beautiful sense the place where everything stops. This journey tonight is a calm and a patient exploration of this ultimate limit. We will travel to the very edge of cold, to the silent and frozen heart of reality itself. We will explore the strange and beautiful quantum world that emerges when matter is cooled to within a hair's breadth of this final stillness. And we will discover the profound and beautiful paradox that this is a destination that we can never, ever truly reach. Before we begin our journey into this realm of ultimate cold and quiet, I would love to know from which part of our own, much warmer and more vibrant world you are joining us tonight. Please write your city or country in the comments below. It is a wonderful way to feel our connection, a global community of curious minds, all sharing this moment of quiet contemplation. And if you enjoy these calm and deep journeys into the fundamental nature of our universe, please consider subscribing to the channel. Your support is the gentle energy that allows these explorations to continue, always calmly, always at the pace of the universe. Our story tonight is not one of simple cooling. It is a journey into the very meaning of what temperature and motion truly are. We will begin by traveling back in time to see how the great minds of science first conceived of this idea of an ultimate cold. And we will follow the story of the great and often dangerous race to try and reach it. From there, we will leave the world of classical physics behind and descend into the strange and wonderful landscape of the quantum realm, a world that emerges only in the deep and profound cold. We will witness the bizarre and beautiful behavior of matter, seeing liquids that can flow uphill without friction, and watching as millions of individual atoms lose their identity and merge together to behave as a single, great, and coherent superatom. And then, we will confront the great and final barrier. We will explore the quiet, the elegant, and the absolute law of thermodynamics that states that while we can get infinitely close to absolute zero, we can never, ever truly arrive. And finally, in our deepest and most profound stop of the journey, we will discover the beautiful and paradoxical truth that even in this place where all motion is supposed to cease, a tiny, a ghostly, and an unconquerable quantum hum of energy must always and forever remain. And so, let us begin our journey, not in the cold, but with our own familiar and intuitive understanding of the beautiful and life-giving fire of heat itself. Our journey to the place where everything stops, to the great and final stillness of absolute zero, must begin not in a modern laboratory, but in the quiet minds of the first scientists who dared to imagine such a place. For most of human history, the concepts of heat and of cold were not seen as part of a single continuous scale. They were thought to be two separate and opposing qualities, fundamental elements of the world, like the difference between wet and dry, or between light and dark. Cold was a substance, a presence, something that could flow into an object to make it feel cold. There was no concept of a limit, a floor, or a bottom to how cold something could be. To ask the question, what is the coldest possible thing, would have been as meaningless as asking, what is the most water-like part of water? The very first step on our long journey, therefore, was the most profound of all. It was the revolutionary idea that the feeling of cold could be captured, could be measured, and could be described with the quiet and the beautiful and the universal language of numbers. This great transformation in our thinking began in the 17th and 18th centuries with the invention of the first true thermometers. In the early 1700s, a German physicist named Daniel Gabriel Fahrenheit sought to create a reliable and a repeatable scale to measure temperature. For his 0 point, he used the coldest temperature he could reliably create in his laboratory, a freezing mixture of ice, water, and ammonium chloride salt. For his other fixed points, he used the temperature at which pure water freezes, which he set at 32 degrees, and the temperature of the healthy human body, which he initially set at 96 degrees. He had created a ladder, a way to quantify the sensation of temperature. For the first time, we could say not just that one thing was colder than another, but precisely how much colder it was. A few decades later, the Swedish astronomer Anders Celsius proposed a simpler, a more elegant, and an ultimately more scientific scale. He based his entire system on the physical properties of a single universal substance, water. He set the freezing point of water at 0 degrees and its boiling point at 100 degrees. This simple and logical 100-step ladder became the great international standard of science. And with these new and powerful tools of measurement, a great and often dangerous race began. Scientists and inventors all over Europe began a quest, a journey down the ladder of cold, to see how low they could possibly go. They developed new and ingenious techniques, using the evaporation of liquids and the expansion of compressed gases to reach ever colder and more extreme temperatures in their laboratories. They succeeded in turning the gas, ammonia, into a liquid. Then they liquefied sulfur dioxide. But the bottom of the ladder was still nowhere in sight. The question remained, was there a bottom at all? The great and beautiful answer to this question came not from an experiment, but from a brilliant and a simple thought experiment, performed in the mind of the great 19th century physicist William Thomson, who is better known to us today as Lord Kelvin. Kelvin was one of the great architects of the science of thermodynamics, the study of heat and of energy, and he was fascinated by the work of the French physicist Jacques Charles, who had discovered a very simple and a very beautiful linear relationship in the behavior of gases. Charles had shown that if you take a gas in a container and you cool it down, its pressure will decrease in a perfectly straight line. Kelvin took this simple, experimental fact, and he extended it with a profound and an imaginative leap of logic. He took the graphs that showed this linear relationship for many different kinds of gases, and in his mind he extended the lines backwards. He asked the great question, if you were to continue to cool a gas colder and colder, and its pressure continued to drop in this perfectly straight line, at what theoretical temperature would its pressure drop all the way to 0? And when he performed this simple graphical extrapolation, he found something truly remarkable. All the lines for all the different gases, no matter how different their properties were at normal temperatures, all converged on the exact same single and theoretical point on his graph. That point was a temperature of minus 273.15 degrees on the Celsius scale. Kelvin realized, with a flash of brilliant insight, that this was not just a mathematical curiosity. It was a deep and a fundamental truth about the nature of reality. He understood that the pressure of a gas is a direct result of the motion of its atoms, and so a point of zero pressure must be the point of zero motion. This, he reasoned, must be the ultimate and the final limit of cold. It must be the bottom of the ladder. He had discovered the location of absolute zero. He then proposed a new and a more logical temperature scale, the Kelvin scale, which begins not at the arbitrary point of freezing water, but at this true and physical and absolute zero. On the Kelvin scale, there are no negative numbers. There is only zero, the place where all motion is supposed to stop. And so, by the end of the 19th century, our journey had its destination. The great philosophical idea of an ultimate cold now had a number. But what did it truly mean for all motion to cease? To answer that, we must now leave the world of human history and descend into the quiet and the invisible and the ever-moving world of the atoms themselves. We have now followed the thread of human curiosity back through time. We have seen how the simple, and then the scientific, act of measuring the cold transformed our entire understanding of the universe. The brilliant imaginative leap of Lord Kelvin extending a simple line on a graph all the way down to its logical conclusion has given us a destination for our journey. We now have a number for the ultimate cold, minus 273.15 degrees Celsius. We have a name for it, absolute zero, and we have a new and more fundamental scale, the Kelvin scale, which begins at this true and physical ground floor of existence. But to truly and deeply appreciate the meaning of this place, we must now embark on another and a much smaller kind of journey. We must leave the world of human-scale thermometers and laboratories behind, and we must shrink ourselves down, in our mind's eye, to the beautiful, the invisible, and the ever-moving world of the atoms themselves. For most of human history, heat and cold were a mystery. They were a feeling, a quality, a kind of invisible fluid that could flow from one object to another. But in the 19th century, a new and profoundly simple idea began to take hold, an idea that is now the very foundation of our understanding. This is the kinetic theory of heat, and it tells us that what we perceive and measure as the temperature of an object is nothing more than a measure of the average motion, the average kinetic energy of the countless tiny atoms and molecules that make up that substance. Heat is not a thing in itself. Heat is motion. Let us imagine this with a simple analogy. Think of the atoms that make up the air in a warm summer room. They are like a vast and a bustling crowd of people in a great public square. They are full of energy, constantly moving and constantly changing direction. The individual atoms are flying about at hundreds of miles per hour, jostling, colliding with one another, and bouncing off the walls of the room. This frantic, chaotic, and high-energy dance of the atoms is what we feel as warmth. Now, let us imagine the air in a cold winter night. The crowd of atoms is still there, but it is a much quieter and a much more sleepy crowd. The individual atoms are moving much more slowly. They are drifting and gently bumping into one another, with far less energy and far less speed. This slow, gentle, and low-energy dance is what we feel as cold. And this dance of the atoms is a rich and a complex one. It is not just a matter of them moving from one place to another. There are, in fact, Three different ways that atoms and molecules can express their thermal energy. Three different kinds of motion. The first is the one we have just described, translational motion. This is the movement of the entire atom or molecule through space, from one point to another. It is the dominant form of motion in a gas. The second form is rotational motion. A simple, single atom can be thought of as a perfect, tiny sphere, so its own personal spin is not a major factor. But most of the substances we know are made of molecules, which are two or more atoms bound together. A water molecule, for instance, is one oxygen atom and two hydrogen atoms, and this little three-part object can spin and tumble through space like a tiny pirouetting dancer. This spinning is another way that the molecule can store and express its heat energy. And the third and most universal form of motion is vibrational motion. The chemical bonds that hold the atoms together within a molecule are not rigid, solid rods. They are much more like flexible and powerful springs, and the atoms at either end of these springs are in a state of constant and furious vibration. They are constantly moving closer together and farther apart, stretching and compressing the bonds that connect them, even in a solid object, like a block of ice or a piece of metal, where the atoms are locked into a rigid, crystalline structure and can no longer translate or rotate freely. They are still not still. Each and every atom is in a state of constant and furious vibration in its fixed position, like a great, silent, and invisible bell that is ringing with a profound thermal energy. And with this new and deep and microscopic understanding of heat as motion, the true meaning of absolute zero, our great and final destination, now snaps into a beautiful and a perfect focus. If heat is motion, then the ultimate cold, the point of zero heat, must be the point of zero motion. Absolute zero is the theoretical temperature at which all of this classical atomic dance is supposed to cease. It is the moment when the translational motion of the atoms in a gas stops. It is the moment when the rotational tumbling of the molecules stops. And it is the moment when the internal vibrational ringing of the atoms themselves finally and completely falls silent. It is the point of perfect classical stillness. It is the quietest and the most profoundly peaceful state that matter can ever hope to achieve. We have now arrived at a new and a much deeper understanding of our final and quietest of all possible destinations. We have journeyed back in time to see how the very idea of absolute zero was first conceived in the brilliant mind of Lord Kelvin. And we have journeyed down into the invisible, microscopic world of the atoms themselves, to understand that this ultimate cold is the theoretical point of a perfect and a profound molecular stillness. We now have a destination marked on our map of reality, a specific and a meaningful point at the very bottom of the cosmic thermometer. And so the next and most practical question of our journey naturally arises. How do we get there? If absolute zero is the destination, what are the steps on the path that can take us into this realm of ultimate quiet? This is the story of the great and often dangerous scientific race to the bottom of the temperature scale. The journey into the cold is governed by one of the most simple and fundamental laws of our universe, a principle that is an echo of our own everyday experience. Heat, as a form of energy, will always and only flow from a hotter object to a colder one. A cup of hot tea will always give its heat away to the cooler air of the room around it. It will never spontaneously draw in more heat from the cool air to become hotter still. This simple, one-way street of energy flow is the foundation of all cooling. To make something cold, you must place it in contact with something that is even colder. And this immediately presents us with a kind of beautiful, logical puzzle. To get very cold, you need a source of something that is already very cold. And to get even colder than that, you need a source of something that is colder still. How then do you take the very first step on this ladder of cold without having a pre-existing source of cold to begin with? The beautiful and ingenious answer to this puzzle lies not in finding a source of cold, but in creating one, by cleverly manipulating the physical properties of matter itself. The great breakthrough that made modern refrigeration possible is the understanding of the deep and intimate relationship between the pressure, the temperature, and the volume of a gas. The simplest form of this is a process we have all experienced: evaporative cooling. When a liquid, like water, evaporates into a gas, it requires a significant amount of energy to do so. It takes this energy in the form of heat from its immediate surroundings, leaving those surroundings cooler. This is why we feel a chill when we step out of a swimming pool on a warm day. But the true workhorse of deep refrigeration is a more powerful and a wonderfully simple phenomenon known as the Joule-Thomson effect. This principle states that when you take a gas that has been compressed to a high pressure and you then allow it to rapidly expand, that expansion causes the gas to cool down dramatically. You can feel this effect yourself with a simple can of compressed air. As you release the gas, allowing it to expand out of the nozzle, the can itself becomes noticeably and sometimes even painfully cold. By harnessing this simple principle, by building engines that could compress a gas, then allow it to cool, and then allow it to expand to become even colder, scientists in the 19th century began their great and epic race to the bottom. The primary goal of this race was to try and liquefy the handful of substances that were still known as the permanent gases. These were gases like oxygen, nitrogen, and hydrogen, which had resisted all of the early attempts to turn them into liquids. Using clever, multi-stage, cascading processes where the liquefaction of an easier gas was used to create a cold bath to help liquefy a more difficult one, scientists began to climb down the ladder of cold, one painstaking step at a time. In the year 1877, a great barrier was broken. Oxygen was liquefied at a temperature of 90 Kelvin. Shortly after, nitrogen was also conquered at 77 Kelvin. The world of the truly and the profoundly cold was now open for exploration. A few decades later, in 1898, the Scottish scientist James Dewar, after a long and a difficult effort, finally succeeded in liquefying the most lightweight of all the gases, hydrogen, reaching the incredible temperature of just 20 Kelvin. The scientific world was now standing at the very doorstep of absolute zero. But one final and most stubborn of all the gases remained. It was a newly discovered element, an inert and a mysterious gas that was found to be present in the sun before it was ever found on Earth. Its name was helium, and it was the final frontier in the great classical race to the bottom. The final victory in this race belongs to the brilliant and the incredibly patient Dutch physicist Heike Kamerlingh Onnes. In his laboratory at the University of Leiden on July 10, 1908, after a long and an exhausting day of running his colossal and complex refrigeration machine, he and his team finally saw the first tiny, shimmering drops of liquid helium begin to form at a temperature of just 4.2 Kelvin. It was a monumental achievement. Humanity had now, through its own brilliant ingenuity, created a temperature that was just a few tiny steps away from the ultimate and the final stillness of absolute zero itself. The great classical journey was complete. But these last few final degrees would prove to be infinitely more difficult to cross than all the hundreds of degrees that had come before. To get any colder, we would have to leave the world of classical physics behind and enter a new, a strange, and a much more wonderful quantum realm. We have now followed the great and heroic age of classical refrigeration to its quiet and triumphant conclusion. We've seen how the brilliant and patient work of scientists in the 19th and early 20th centuries allowed us to descend the great ladder of cold, one painstaking and often dangerous step at a time. The final victory of this classical era, the liquefaction of helium by Heike Kamerlingh Onnes in 1908, brought humanity to within a mere 4.2 degrees of our ultimate destination. We were now standing at the very doorstep of absolute zero, and it was a truly extraordinary and an almost unimaginably cold place. But to travel across those last, final 4 degrees would prove to be an infinitely more difficult and more subtle challenge than traveling the first 400. To go any further, to get any colder, we would have to leave the familiar, common-sense world of classical physics behind entirely. We would have to invent a new kind of science and a new kind of tool to enter the strange, the beautiful, and the ghostly world of the quantum realm. To understand why this new approach was necessary, we must first deepen our understanding of what an atom truly is. In our last chapter, we used the simple and helpful analogy of atoms as tiny classical billiard balls, bouncing and vibrating with thermal energy, and at normal everyday temperatures. This is a perfectly good and a useful way to think about them. But as we approach the profound and almost absolute cold just a few degrees above 0 Kelvin, this simple picture begins to break down. We must now embrace one of the most beautiful and most mysterious truths of modern physics, the idea of wave-particle duality. This principle, first proposed by the physicist Louis de Broglie, tells us that all particles of matter in the universe, from the smallest electron to the largest galaxy, have a wave-like nature. Every object has a wavelength, a tiny quantum hum of existence. For large and for hot, and for fast-moving objects, this wavelength is so incredibly and so ridiculously small that it is completely and utterly irrelevant. But as a particle of matter gets colder, and as its motion slows down, its quantum wavelength gets longer and longer and longer. Let us try to picture this with another simple analogy. Imagine that a single, hot, and fast-moving atom is like a tiny, tightly wound ball of yarn. It is a compact, a well-defined, and a particle-like object. But as we begin to cool this atom down, as we remove its energy and slow its motion, it is as if we have begun to gently and slowly unravel that ball of yarn. The atom's wave-like nature begins to spread out. It becomes a less defined, a more diffuse, and a more blurry object. The quest for absolute zero, then, is not just a quest to stop the motion of particles. It is, from this deeper quantum perspective, a quest to make the quantum waves of matter as long, as calm, and as spread out as possible. And this is where the new frontier of cold truly begins. At the relatively hot temperature of 4 Kelvin, in a flask of liquid helium, the atoms are still moving slowly enough and are still compact enough that they are like a sparse collection of tiny, distinct billiard balls. The average distance between them is still very large compared to the size of their own tiny quantum wavelengths. But as we continue to cool a gas of atoms down into the realm of millionths, or even billionths of a single Kelvin above absolute zero, two things happen. The atoms are moving at an almost impossibly slow speed, some as slow as a snail's pace, and their quantum waves, their de Broglie wavelengths, have now stretched out and become enormous. And then a magical and a transformative moment occurs. The gas becomes so cold and the atoms so slow that their great, blurry, and spread out waves begin to overlap with one another. This is the moment that the classical world ends and the quantum world begins. The gas is no longer a collection of billions of tiny, individual, and distinct particles. The atoms begin to lose their individuality. They begin to merge into a single, vast, and coherent collective quantum state. It is a strange and a beautiful new form of matter, a quantum soup, where each atom is everywhere at once and is in perfect and unspoken communication with every other atom. To get any colder, we can no longer think about simply removing heat from a substance. We must now find a way to gently and directly manipulate this strange, new, collective quantum state. The old tools of gas compression and expansion are no longer precise enough for this delicate work. We need a new and a more gentle kind of tool, a way to reach out and touch the individual atoms themselves, a kind of atomic tweezer that can slow them down one by one. We need to invent a form of atomic molasses. We need to learn how to cool with light itself. We have followed the great classical race to the bottom of the temperature scale and have arrived at the final frontier of that journey. We have reached the incredible temperature of liquid helium, just 4.2 degrees above the absolute and final stillness of 0 Kelvin. We have also learned that to get any colder, to cross this final, vast, and difficult gulf, the old, classical tools of refrigeration are no longer enough. We have entered a new and a strange landscape, the quiet and the beautiful landscape of the quantum realm. In this world, atoms are no longer tiny, solid billiard balls, but are vast, blurry, and overlapping waves. And to cool them down any further, we can no longer think in terms of simply removing heat. We must now find a new and an impossibly delicate way to gently and directly slow down the motion of the individual atoms themselves. We need a new kind of tool. And the beautiful, the paradoxical, and the almost magical tool that science has invented for this task is the most energetic and the most vibrant thing we know. To reach the ultimate cold, we have learned how to cool with light itself. This idea, at first, sounds like a profound and a beautiful contradiction. How can you use light, a form of pure energy, to make something colder? How can you use a laser, a tool that we associate with intense and concentrated heat, a tool that can cut through steel, to bring a collection of atoms to a near-perfect and an absolute standstill? The answer lies in one of the most simple and fundamental properties of light. The individual particles of light, the photons, have no mass, but they do have momentum. A single photon is like a tiny, invisible, and massless bullet. And when it strikes an atom, it gives that atom a tiny and a very gentle push. Let us imagine a single, large, and slow-moving bowling ball. This is our atom. Now, imagine you have a machine that can fire a constant stream of billions of tiny and almost weightless ping-pong balls. These are our photons. A single ping-pong ball striking the great, heavy bowling ball will have almost no effect at all. But if you can fire a continuous and a powerful stream of these ping-pong balls, and if you can aim them perfectly to always be hitting the bowling ball on its front side, this relentless and gentle and persistent barrage will slowly but surely begin to slow the bowling ball down. This is the simple and the beautiful principle behind the Nobel Prize-winning technique of laser cooling. Here is how this beautiful and almost magical process works in practice. Scientists take a small and a very sparse cloud of atoms, perhaps a few million of them, and they place them in a perfect vacuum chamber. Then, they fire 6 powerful laser beams at this cloud, one from every possible direction. One from the left, one from the right, one from the front, one from the back, one from above, and one from below. The cloud of atoms is now completely surrounded by a perfect and an invisible cage of light. And now we come to the brilliant and the clever heart of the technique. The lasers are all tuned to a very specific frequency of light. They are tuned to a frequency that is just slightly below the natural resonant frequency at which the atoms like to absorb light. And this is where the magic of the Doppler effect comes into play. As we have learned, an atom that is moving towards a source of light will perceive that light as being slightly higher in frequency, a process known as a blue shift. And so, an atom in our cloud, as it moves towards one of the 6 laser beams, will see that laser's light blue shifted up into its perfect and preferred absorption frequency. The atom will, therefore, absorb a photon from the beam it is heading towards. When it absorbs that photon, it gets a tiny but a significant kick in the opposite direction, slowing it down. But what about the laser beam that is behind it, the one it is moving away from? The light from that beam will be perceived by the atom as being redshifted to an even lower frequency, even further away from its absorption sweet spot. And so the atom will almost never absorb a photon from a laser it is moving away from. The net result of this beautiful and elegant dance is that no matter which direction an atom tries to move, it is always and most effectively being pushed back by the laser beam that it's running into. It is as if the atoms are suddenly trying to move through a thick and a gooey and an invisible liquid. This is why the technique is often poetically referred to as optical molasses. This thick and sticky and gentle headwind of light, coming from all 6 directions at once, very, very rapidly slows the entire cloud of atoms down, bringing them to an almost perfect standstill. This process of laser cooling can chill a cloud of atoms down to a temperature of just a few microkelvin, a few millionths of a single degree above the final stillness of absolute zero. And to cross the final and the most difficult of all the remaining gaps, scientists employ one final and an even older technique, evaporative cooling. After the atoms have been cooled and trapped by the lasers, they are held in a silent and an invisible magnetic trap. And then, the scientists slowly and gently lower the power of this magnetic field. This is like slowly lowering the walls of a bowl that is filled with a hot liquid. As the walls are lowered, the very hottest and the most energetic of all the atoms are able to escape and fly away, just like the hottest molecules of water evaporating as steam from a cup of tea. And every single time the hottest atoms leave, the average temperature of the atoms that are left behind becomes colder and colder and colder. By this final and gentle and incredibly precise act of evaporation, we have now, finally, arrived at our destination. We have reached the coldest place in the entire known universe. We have now, in our shared and quiet journey, arrived at the very edge of the ultimate cold. Through the beautiful and almost magical dance of laser cooling and the patient final step of evaporative cooling, we have followed the path of modern science to a place of almost unimaginable stillness. We have reached a temperature that is just a few fleeting billionths of a single degree above the final and absolute zero. We are now in the coldest known place in the entire observable universe. The frantic thermal dance of the atoms has been slowed to an almost perfect and complete standstill. And it is here, in this realm of profound and unprecedented quiet, that the familiar classical world of our everyday experience completely and utterly dissolves, and the deep, the strange, and the truly wonderful nature of the quantum realm reveals itself in its full and majestic glory. It is here that matter, in its final and most serene state, reveals a fifth and a final state of being. We are all familiar with the 4 states of matter. We know of solids, where atoms are locked into a rigid, vibrating lattice. We know of liquids, where they are free to flow past one another. We know of gases, where they fly about in a state of chaotic freedom. And we know of plasmas, the superheated state of matter, where electrons are torn from their atoms in the hearts of stars. But in this realm of the ultimate cold, a new and a profoundly different state of matter emerges, a state that was first predicted as a purely theoretical idea by the combined work of Satyendra Nath Bose and Albert Einstein in the 1920s, some 70 years before humanity would ever develop the technology to actually create it. This fifth and final state of matter is known as the Bose-Einstein condensate. To understand this strange and beautiful new reality, we must return to the idea of an atom as both a particle and a wave. As we have learned, the colder an atom gets, the slower it moves, and the longer and more spread out its quantum wavelength becomes. In the final nano-Kelvin temperatures that we have now reached, the individual wave-like blurs of the atoms have now stretched out to become enormous, far larger than the physical size of the atoms themselves. And in the small, dense cloud of our magnetic trap, these great blurry waves have now begun to overlap with one another so completely that a profound quantum identity crisis occurs. The universe, in a very real sense, can no longer tell the individual atoms apart. Imagine for a moment a great and crowded ballroom filled with thousands of individual dancers. At a normal temperature, each dancer is performing their own unique and energetic dance. This is our gas. As we cool the room down, the dancers all begin to move in a beautiful and a graceful slow motion, but they are still individuals, each with their own distinct identity. This is our ultra-cold gas. But as we cross the final critical temperature threshold, something truly magical happens. All at once, all of the thousands of individual dancers, as if they are suddenly hearing a new and a universal piece of music, abandon their own individual dances, and they all begin to perform the exact same, single and perfectly synchronized set of movements. Their individual identities have been lost. They have ceased to be a crowd of individuals and have instead merged into a single, vast, coherent, and collective performance. This is what happens in a Bose-Einstein condensate. The individual atoms have lost their identity. Their once separate quantum wave functions have all merged together, and the entire cloud of millions of atoms has now condensed into a single, vast, and unified quantum entity. It is a single, colossal matter wave. It has become a superatom. All of the millions of atoms that make up this new object are now behaving as one. They are in a state of perfect and a beautiful coherence. If you were to gently push on one side of this condensate, the entire cloud would respond instantly as a single object. It is the ultimate expression of quantum unity, the place where the many, finally and completely, become the one. This beautiful and bizarre state of matter was first created in a laboratory in 1995 by the physicists Eric Cornell and Carl Wieman, an almost miraculous achievement of experimental science that was rightly awarded the Nobel Prize. And it is in this strange, new, and superatomic state that the weird and wonderful rules of the quantum world, which are normally hidden away at the microscopic scale, become manifest on a scale that we can actually see and interact with. A Bose-Einstein condensate is a piece of the quantum world, magnified 1,000,000 times over. It is matter in its quietest, its most coherent, and its most unified and peaceful state. And it is the first, great, and beautiful secret that the universe reveals to us in the final and most profound stillness of the ultimate cold. We have now, in our shared and quiet journey, witnessed the birth of a new and a truly extraordinary state of matter. We have seen how, in the coldest place in the known universe, just a few billionths of a degree above the final stillness of absolute zero, a cloud of individual atoms can lose their identity and merge into a single, vast, and coherent quantum entity, a superatom known as a Bose-Einstein condensate. This is the ultimate expression of the quantum world made manifest on a macroscopic scale, a beautiful and a profound secret that the universe reveals only in a state of almost perfect quiet. But this strange and beautiful quantum behavior is not limited to these sparse and artificially created clouds of gas. The journey into the deep cold reveals another, and in some ways, an even more magical and a more bizarre phenomenon, one that occurs in a substance that is much more familiar to us. Let us now return to the story of the last and the most stubborn of all the permanent gases, the story of liquid helium. As we learned, the great Dutch physicist Heike Kamerlingh-Onnes first succeeded in liquefying helium in the year 1908, reaching a temperature of just 4.2 Kelvin. In the years that followed, physicists all over the world began to study the properties of this strange and incredibly cold new liquid. And they soon discovered that helium is a truly unique and a truly remarkable element. It is the only known substance in the entire universe that will not freeze into a solid at normal atmospheric pressure, no matter how cold you make it. You can cool it all the way down to absolute zero, and it will remain a liquid. This strange inability to freeze is itself a purely quantum mechanical effect, a result of the atom's light weight and the quiet but persistent hum of its zero-point energy. But the greatest of all of liquid helium's secrets is revealed as we cool it down below its boiling point. Let us imagine we have a small glass container of liquid helium at a temperature of 4 Kelvin. It is a clear and a normal, albeit an incredibly cold liquid. And because we are in a vacuum, it is boiling furiously, bubbling and churning with a violent energy. Now, let us begin to slowly and gently pump away the vapor above the liquid, causing it to cool down even further. As its temperature drops past 3 Kelvin and then begins to approach 2, it continues to boil with this same furious energy. But then, as the temperature crosses a very specific and a very magical threshold, a temperature of 2.17 Kelvin, a point that is known as the lambda point, something truly extraordinary and completely silent happens. All at once, in an instant, all of the boiling completely and utterly stops. The liquid becomes as still, as clear, and as quiet as a perfect sheet of glass. It has, in a quiet and a beautiful phase transition, transformed into a new and a deeply strange state of matter. It has become a superfluid. A superfluid is a liquid that flows without any friction. It has a viscosity of exactly 0. To understand how strange this is, imagine you were to take a spoon and stir a cup of hot coffee. When you remove the spoon, the swirling vortex in the coffee will slow down and disappear in a matter of seconds, its energy dissipated by the friction between the liquid molecules. But if you were to gently stir a cup of superfluid helium, that small vortex would continue to spin in a perfect and a silent whirlpool forever. There is no internal friction to slow it down. It is a state of perpetual, frictionless motion. And from this one simple and profound property of zero viscosity, a host of other, seemingly magical behaviors emerge. A superfluid is the ultimate escape artist. It can leak through microscopic cracks, pores that are only a few atoms wide, that would be perfectly and completely impenetrable to any normal liquid. This is a phenomenon known as a superleak. But the most famous and most visually spectacular of all its properties is a behavior known as film creeping. If you were to place an empty, open container into a bath of superfluid helium, you would witness something that seems to defy the laws of gravity itself. A thin and almost invisible film of the superfluid, only a few hundred atoms thick, would spontaneously begin to crawl up the outside walls of the empty container. And then, down the inside walls until it had filled the container to the exact same level as the bath outside. And if you were to then lift that container up out of the bath, the film would reverse its journey, crawling back up the inside of the container, over the lip, and down the outside, dripping back into the bath until the container was once again completely empty. This strange and beautiful behavior is not magic. It is the quantum world made visible. For a superfluid, like a Bose-Einstein condensate, is a macroscopic quantum state. The individual helium atoms have all condensed into their lowest possible energy state and are now behaving as a single, vast, and coherent quantum entity. The liquid is now one great superatom, and so it moves not as a collection of individual particles, but as a single, unified wave. The world near absolute zero is a place where the familiar, classical rules of our world are beautifully and quietly suspended, and the deep and the strange and the wonderful rules of the quantum realm rise up to take their place. We have now, in our quiet exploration of the ultimate cold, witnessed the universe reveal two of its most profound and beautiful secrets. We have seen how a sparse gas of atoms, when cooled to a near-perfect standstill, can lose its individuality and condense into a single, vast, and coherent superatom. And we have seen how a liquid, the strange and unique element of helium, when cooled below a critical point, can transform into a magical and a frictionless superfluid. A substance that can flow uphill and defy the very concept of viscosity. We have seen the quantum world emerge in the realm of gases and in the realm of liquids. And now we must complete this beautiful trilogy. We must turn our attention to the third and most familiar state of matter. We must ask, what strange and wonderful secrets does the universe reveal when a solid is brought down into this world of profound and absolute quiet? The answer is a phenomenon as beautiful, as paradoxical, and as powerful as the others. It is the discovery of the perfect and the effortless path. It is the phenomenon of superconductivity. To understand this, let us first consider the simple and familiar flow of electricity. An electrical current in a normal conductive metal, like a piece of copper wire, is simply a great river of electrons flowing through the fixed, crystalline lattice of the copper atoms. But this journey is not an easy one. In a normal metal, even one that is very cold, the atoms of the lattice are not perfectly still. They are in a state of constant thermal vibration, like a great and restless crowd, and the individual electrons, as they try to push their way through this crowded and jostling lattice, are constantly bumping into these vibrating atoms. Each one of these tiny, almost infinite number of collisions slows the electron down and scatters it from its path. This is the source of electrical resistance. It is a kind of atomic scale friction, and this friction is why our wires get warm, and why a significant amount of energy is always lost when we try to transport electricity from one place to another. For a long time, scientists wondered what would happen to this resistance as a material got colder and colder. The logical assumption was that as the thermal vibrations of the atoms quieted down, the resistance would get lower and lower, but that it would likely level off at some small residual value due to imperfections in the metal. And in the year 1911, the same great Dutch physicist who had first liquefied helium, Heike Kamerlingh-Onnes, decided to find out. Using his precious newly created liquid helium as a coolant, he took a sample of solid, frozen mercury, and he began to measure its resistance as he cooled it down to the coldest temperatures ever achieved on Earth. At first, the results were exactly as he had expected. The resistance of the mercury dropped steadily and smoothly as the temperature went down. But then, as he cooled the mercury down to the critical temperature of just 4.2 Kelvin, the boiling point of helium, his sensitive instruments suddenly and inexplicably seemed to break. The electrical resistance of the wire did not just get very, very low. It suddenly and completely vanished. It dropped to a perfect and an absolute and a scientifically impossible zero. He had not broken his instruments. He had broken the laws of classical physics. He had discovered superconductivity. A superconductor is a material that, when cooled below a critical temperature, can conduct electricity with a perfect and a beautiful efficiency. If you were to start a loop of electrical current flowing in a closed ring of superconducting wire, that current would, in theory, continue to flow, undiminished, forever. It is a perpetual and an effortless and a perfect atomic river. But the most famous and most visually spectacular property of a superconductor is its strange and beautiful relationship with magnetic fields, a phenomenon known as the Meissner effect. A superconductor will actively and perfectly expel all magnetic fields from its interior, and this leads to one of the most magical demonstrations in all of physics. If you take a small, powerful magnet and you try to lower it onto a piece of superconducting material that is being cooled in a bath of liquid nitrogen, the magnet will not touch the surface. Instead, as it gets close, the superconductor will generate its own perfect and opposing magnetic field, and the magnet will simply lift up and float, weightlessly and perfectly, and with an almost supernatural stability above the surface. This beautiful and seemingly impossible levitation is, like the other phenomena of the deep cold, a direct manifestation of the quantum world on a large scale. In a normal metal, the electrons move as individuals, but in a superconductor, at these incredibly low temperatures, the electrons, which normally repel each other, find a way to team up in pairs, known as Cooper pairs. One electron, as it moves through the crystal lattice, causes a tiny and a very fleeting distortion in the lattice, a small positive ripple. A second electron, a moment later, is attracted to this ripple and becomes loosely but coherently bound to the first. And these new paired-up electrons can now, like the atoms in a Bose-Einstein condensate, all fall into a single, vast, and unified quantum state. This great, collective, and coherent superfluid of electron pairs can then flow through the atomic lattice as a single entity, a great quantum wave that moves without interacting, without colliding, and without losing any energy at all. It is the third and final great secret of the ultimate cold, the secret of the perfect and the frictionless path. Our journey into the cold has brought us to the very edge of the ultimate quiet. Through the classical brute force methods of gas liquefaction, we descended the great ladder of temperature to within a few scant degrees of our destination. And then, with the beautiful and almost magical assistance of laser cooling and the patient final whisper of evaporative cooling, we have learned how to cross the final quantum gulf, arriving at a temperature that is just a few precious billionths of a single degree above the final floor of existence. It would seem, after this long and brilliant journey, that our final destination is within our grasp. It feels as though we should be able to take one final, easy step and arrive at the perfect and absolute stillness of 0 Kelvin. And yet, it is here, at the very doorstep of our goal, that the universe presents us with a final, a beautiful, and an absolutely impassable barrier. It is a fundamental law of our reality, a quiet and an elegant principle known as the third law of thermodynamics. To understand this final law, let us briefly and quietly recall its two more famous older siblings. The first law of thermodynamics is the great law of conservation. It tells us that energy cannot be created or destroyed, only changed from one form to another. The second law of thermodynamics is the great law of entropy and of time's arrow. It tells us that in any isolated system, the total amount of disorder or entropy will always increase over time. It is the law that explains why a hot cup of tea will always cool down, and why a fallen glass will never spontaneously reassemble itself. These two laws are the great governing principles of energy and of change in our universe. But it is the third and the quietest of these laws that concerns our final journey into the cold. The third law of thermodynamics can be stated in a number of ways, but its most simple and most profound consequence for our journey is this: it is impossible to reach a temperature of absolute zero in a finite number of steps. This law is not a statement about our technological limitations. It is not a prediction that we will never be clever enough to build a perfect refrigerator. It is a fundamental and an absolute statement about the very nature of heat and of energy. It tells us that absolute zero is a destination that we can get infinitely close to, but can never, ever truly reach. To understand why this must be so, we can think of the great, ancient, and beautiful paradox of the Greek philosopher Zeno. Imagine you want to walk across a room. To get to the other side, you must first travel half the distance. And from that new point, to get to the end, you must first travel half of the remaining distance. And then half of that new, smaller remaining distance. And so on forever. You are always getting closer to your destination. But because you are always only covering half of the remaining distance, you must take an infinite number of ever smaller steps. And so, in this strange and beautiful logical paradox, you can never, in theory, actually arrive at the other side of the woo. The journey to absolute zero is a kind of physical, thermodynamic version of this paradox. Every process of cooling, every clever machine we can build, can only ever remove a certain fraction of the remaining heat energy from a system. In the early stages of our journey, when there's a lot of heat, removing a fraction of it is a relatively easy and an efficient process. But as our object gets colder and colder, and the amount of remaining heat energy becomes smaller and smaller, the fraction of that heat that we can remove in each successive step also becomes smaller and smaller. The journey down the final few degrees, and then the final few millionths of a degree, becomes a journey of an infinite number of ever more difficult and ever less efficient steps. We are always getting closer, but we can never take the final step that would remove the last, final, infinitesimal remnant of heat and land us squarely on the shores of zero. This law can also be understood from the perspective of entropy. Entropy, as we know, is a measure of disorder. To cool a substance down is to remove its entropy, to make its atoms more orderly and still. The third law also states that the entropy of a perfect crystalline substance at absolute zero is exactly zero. It is a state of perfect and of absolute order. The journey to absolute zero, then, is a journey to remove all of the entropy, all of the disorder, from a piece of matter. And the third law tells us that this too is an impossibility. You can never create a system of perfect and of absolute order. And so, our final destination has been transformed. Absolute zero is not a real and a physical and an attainable place. It is a concept. It is a limit. It is a perfect and a beautiful and a deeply peaceful ideal that is forever and beautifully just beyond our reach. Our quiet and patient journey into the cold has now brought us to a place of beautiful and profound limitation. We have followed the great, century-long race to the bottom of the temperature scale, and we have seen how, with our most brilliant and ingenious technologies, we can arrive at the very doorstep of our final destination. We can now create temperatures that are just a few fleeting billionths of a single degree away from the ultimate cold. And yet, we have also come to understand the great and final law that stands as a guardian at this final gate. The third law of thermodynamics has taught us that absolute zero is a destination that we can approach with an almost infinite closeness, but can never, ever truly reach. The journey, it seems, is an infinite one. The final, perfect stillness is a beautiful but an unattainable dream. But now, as we stand here, at this quiet and final frontier of our understanding, the universe is preparing to reveal its last, its most subtle, and its most beautiful secret about the nature of the ultimate cold. The story so far has been based on one fundamental assumption, that absolute zero is indeed a place of perfect and of absolute stillness. But what if this assumption, the very foundation of our journey, is itself not entirely true? Even if we could somehow bypass the third law and arrive at a temperature of exactly 0 Kelvin, the universe would still not be perfectly still. This is the final and the most profound paradox of the deep cold, a beautiful and a necessary truth that is whispered to us from the very heart of the quantum realm. To understand this final secret, we must become acquainted with one of the most famous and most fundamental principles of quantum mechanics. It is a law known as the Heisenberg uncertainty principle. In its simplest and most gentle form, this principle states that there is a fundamental and an unavoidable trade-off in the universe between knowing a particle's exact position and knowing its exact momentum, which is its motion. The more precisely you know one of these things, the less precisely you can possibly know the other. Let us imagine this with a simple analogy. Imagine you are trying to take a photograph of a single, fast-moving car. If you use an incredibly fast shutter speed, you can capture a single, frozen instant of time. You will get a photograph that is perfectly sharp and clear. You will know the car's exact position at that one specific moment. But because the image is frozen, you will have no information at all about how fast it was going or in which direction. Now, imagine you take another photograph, but this time you use a long exposure. You will get a photograph that shows a long, blurry streak of light. This streak tells you a great deal about the car's motion, its speed, and its direction. But you now have no idea where the car was with any precision at any single moment in time. There is a fundamental trade-off. You can have a clear picture of position or a clear picture of motion, but you can never, with perfect and absolute precision, have both at the same time. The Heisenberg uncertainty principle tells us that this is not a limitation of our cameras or our measuring devices. It is a fundamental and an unerasable property of the universe itself. And this beautiful and strange principle has a profound and an unavoidable consequence for our journey to absolute zero. Let us imagine for a moment that a particle of matter could, in fact, be cooled all the way down to a perfect and an absolute 0 Kelvin. If this were to happen, it would be in a state of perfect and absolute rest. Its motion, its momentum would be exactly and precisely 0. We would know its momentum with perfect and absolute certainty. But the uncertainty principle tells us that if we know a particle's momentum with perfect certainty, then we must have an infinite and a total uncertainty about its position. A particle that is perfectly still would, in a very real and a very quantum mechanical sense, have to be everywhere in the universe at once. This is a physical and a logical impossibility. And so, to avoid this beautiful paradox, to ensure that the universe remains a coherent and a sensible place, a particle can never ever be perfectly still. It must always and forever retain a tiny, an irreducible, and an unconquerable amount of motion. This minimum and unavoidable and absolutely fundamental amount of energy that a particle must have, even at a temperature of absolute 0, is known as the zero-point energy. It is the fundamental quantum hum of the universe. It is the gentle, the ceaseless, and the beautiful, vibrational breath of the fabric of reality itself. It is the quiet, background whisper of existence that can never, ever be silenced. And so, we have arrived at the final and the most beautiful revelation of our journey. The place where everything stops is not in fact a place of perfect stillness. It is simply the place where all the thermal motion, all the chaotic and the transferable motion of heat has been completely and totally removed. But the fundamental, a quantum, the zero-point motion of the universe must always and forever remain. The great, quiet, and beautiful silence at the bottom of the universe is not the silence of a thing that is dead. It is the quiet and the perfect and the harmonious hum of a thing that is and will always be, fundamentally and beautifully alive. Our journey to the heart of the ultimate cold has led us to a place of the most beautiful and profound paradox. We have followed the great and absolute third law of thermodynamics and have learned that the perfect stillness of absolute zero is a destination that we can never, ever truly reach. And then we have descended even deeper into the strange and beautiful heart of the quantum realm and have learned from the Heisenberg uncertainty principle that even if we could get there, our destination would not be perfectly still after all. The universe, it seems, is forever imbued with a quiet, a gentle, and an unconquerable quantum hum of zero-point energy. The place where everything stops is, in fact, a place where a fundamental and a beautiful kind of motion must always and forever remain. And so, we have now completed our theoretical exploration. We have learned the history, the science, and the deep quantum philosophy of the absolute limit of cold. And for the final stages of our journey tonight, let us now leave the quiet and the controlled world of the human laboratory and let us embark on one final cosmic tour. Let us ask the question, where, in the grand and majestic expanse of the natural universe, is the coldest of all places? Our first and most intuitive guess would be the great, empty, and silent void of deep intergalactic space. The farther we travel from the warmth of our sun and all the other stars, the colder it should get. It would seem logical that the great empty spaces between the galaxies, the places of the most profound and the most perfect nothingness, would also be the places of the most profound and the most perfect cold. But this is not the case. As we learned in our previous journey, the universe is not truly dark and it is not truly empty. It is filled with a faint, a perfect, and a pervasive afterglow from its own fiery creation. This is the cosmic microwave background, the faint and now incredibly cold echo of the Big Bang itself. This ancient and beautiful and universal light, this bath of primordial photons, fills every single corner of the cosmos, and it gives the universe a base and a minimum temperature. The temperature of the emptiest space is not 0 Kelvin. It is 2.725 Kelvin. The universe, at its heart, is not absolutely cold. It is filled with a faint and an eternal warmth from its own birth. So, if the emptiest space is not the coldest place, where is? To find a place in the universe that is naturally colder than this cosmic background, we would have to find a place that is somehow actively cooling itself down, a place that is producing its own natural refrigeration. And in the year 1995, astronomers using a radio telescope in Chile found just such a place. It is a young and a beautiful and a truly extraordinary planetary nebula located some 5,000 light-years away from us in the constellation of Centaurus. It is called the Boomerang Nebula. The Boomerang Nebula is the coldest natural place that we have ever discovered in the entire known universe. At its heart is a dying star, very much like our own sun will be in its final stages. And this dying star is expelling its outer layers of gas into space in a powerful and an incredibly fast stellar wind. The gas is being blown outwards at a speed of more than 164 kilometers per second. And just like the gas that is released from a compressed can of air, this rapid and violent expansion is causing the gas of the nebula to cool down dramatically. The Boomerang Nebula is, in a very real sense, a colossal and a cosmic scale refrigerator. It is cooling itself down so effectively that its internal temperature has dropped to just 1 Kelvin. It is a place that is more than 1.5 degrees colder than the faint background radiation of space, background warmth of the universe that surrounds it. It is the one natural place we know of where the universe has, through its own beautiful and dynamic processes, found a way to become even quieter and even stiller than the echo of its own creation. And as we look closer to home, into our own solar system, we also find pockets of profound and of natural cold. In the permanently shadowed craters at the poles of our own moon, places that have not seen a single ray of direct sunlight for more than 1 billion years, the temperatures can plummet to as low as 25 Kelvin. And in the great, distant, and silent realm of the Oort cloud, the primordial snowballs that will one day become our comets are drifting in a state of perpetual deep freeze at a temperature of only about 5 to 10 Kelvin. But here we find a final and a humbling reversal. Nature, in its grandest and most efficient refrigerator, the Boomerang Nebula, can achieve the incredible temperature of 1 Kelvin. But humanity, in our small and our quiet and our patient laboratories, has now far surpassed this. With the beautiful and elegant dance of our lasers and our magnetic traps, we have learned how to create a stillness that is 1 billion times colder still. In our quiet and tireless quest to understand the universe, we have, in this one small way, learned how to become even quieter than the universe itself. Our long and quiet journey has now taken us to the very bottom of the universe. We have traveled together from our own warm and intuitive human experience of the cold down through the heroic history of its scientific exploration and into the strange, the beautiful, and the profoundly weird quantum realm that exists at the very edge of absolute zero. We have seen how this ultimate cold transforms matter into new and almost magical states from the coherent, unified superatom of a Bose-Einstein condensate to the frictionless, gravity-defying flow of a superfluid. We have explored the coldest natural places in the cosmos, and we have learned that our own quiet laboratories are the coldest places of all. And we have, in the end, been met by the two great and final paradoxes of the cold. The first is that the destination of absolute zero is a place that we can never ever truly reach. And the second is that even if we could, it is a place that is not and can never be perfectly still. The scientific exploration is now complete, and we are left, in these final quiet moments of our journey, to reflect on the deeper and more philosophical message of this great cosmic limit. What is the wisdom that is being whispered to us from this place of ultimate quiet? What does the existence of this beautiful and unattainable destination teach us about our universe and about ourselves? The first and perhaps most profound of these lessons is a simple message about the nature of our reality. The existence of a fundamental floor to temperature, a hard and an absolute limit of cold, is a quiet and a powerful statement that our universe is a place of rules. It is a cosmos that is governed by a deep, an elegant, and an ultimately knowable physical law. The universe is not a place of infinite and chaotic possibility. It has a structure. It has boundaries. And it is these very limits, these beautiful and elegant rules, that are the source of its stability, and the very reason that complex and beautiful things, like stars and planets and living beings, can exist at all. A universe without limits would be a universe of pure and of featureless chaos. The great absolute limit of the cold is not a prison wall. It is a foundational pillar, a source of the quiet and the order and the beautiful predictability that allows our own warm and vibrant existence to be possible. The second lesson is a gentle and a beautiful meditation on the nature of a journey. The third law of thermodynamics, in its quiet wisdom, has taught us that the journey to absolute zero is an infinite one. It is an asymptotic quest, a destination that we can get ever and ever closer to, but can never, in a finite number of steps, truly arrive at. And in this, we'll find a perfect and a beautiful metaphor for so many of the most meaningful journeys in our own lives. The quest for perfect knowledge, for perfect understanding, or for perfect peace is also an infinite one. There is no final and absolute destination where the journey is over, and the universe, in its deep wisdom, is teaching us that the beauty is not found in the finality of the arrival. The beauty is found in the journey itself. It is found in the patient and the humble and the unending process of getting ever and ever closer to a more perfect and a more peaceful state. And the final and most beautiful lesson of all comes to us from that deep and unconquerable and eternal quantum hum of the zero-point energy. We began this journey with a simple and an intuitive idea that the place where everything stops would be a place of a perfect and a dead stillness. And we have ended our journey with the profound and the beautiful realization that nothing can ever truly stop. The universe at its very foundation, at its coldest and its quietest, and its most empty, is still and always will be alive with a gentle and a silent and a beautiful vibrational energy. Existence at its very heart is not a state of stillness. It is a state of motion. The great, silent, and final peace at the bottom of the universe is not the silence of an ending. It is the quiet and the harmonious and the eternal hum of being itself. And this is the most hopeful and the most life-affirming of all possible messages. It is a quiet and a final reassurance from the very foundation of reality itself that the universe is and will always be fundamentally and beautifully alive. Our long and quiet journey has now reached its final and most peaceful destination. We have traveled to the very bottom of the cosmic thermometer, to the beautiful, the unattainable, and the deeply mysterious realm of absolute zero. We have discovered that the place where everything stops is not a place of dead and empty silence, but is instead a place that is alive with the gentle and the eternal and the unconquerable quantum hum of the universe itself. The great scientific and philosophical exploration is now complete. We have returned with the beautiful and calming wisdom that the universe, at its very heart, is a place of quiet and of order and of a deep and an abiding peace. And now, the only journey that remains is the most simple, the most gentle, and the most natural journey of all. It is the final, quiet, and effortless descent into the deep and healing universe of your own sleep. And so, as you rest here now, in the comfort and the safety of your own quiet space, you can give yourself the great and final gift of letting go. Allow the story of the absolute cold and all of its vast and complex ideas to gently dissolve like a fine and an ancient mist. The words and the images have served their purpose. They have been the vessel that has carried us to this quiet and peaceful shore. And now you can step out of the vessel and rest. There are no more questions to be answered tonight. There are no more mysteries to be solved. There is only the deep and profound silence that the story leaves behind, and the simple, gentle, and present reality of your own being at rest. Let us begin this final, gentle journey by bringing our awareness into the body. Let us start with the very tips of your toes, and from there, imagine a slow, soft, and gentle wave of stillness beginning to move upwards. Feel this gentle wave as it flows into your feet and then into your ankles, washing away any and all of the day's motion, allowing them to feel heavy, warm, and completely at rest. Allow this soft, warm wave of stillness to continue its journey up into your lower legs, and then into your knees, and then into your thighs. With every gentle breath out, feel your legs becoming heavier and heavier, sinking comfortably and safely into the surface beneath you. You do not need to hold them up any longer. You can let them go completely. Now feel this gentle, warm wave as it flows into the base of your spine, into your hips, and into your pelvic area. This is the great, stable center of your body, and you can allow it now to feel completely and utterly supported. Let the wave of relaxation continue its slow and patient journey upwards, into your lower back, and then into your middle back, and then all the way up to your shoulders, releasing every small knot of tension, every trace of the day's posture, allowing your entire back to melt into a state of deep and profound comfort. Bring your awareness to your stomach and your chest, and just notice the gentle, natural, and easy rhythm of your own breathing. The soft rise on the inhale and the gentle fall on the exhale. This is the quiet, life-giving pulse of your own personal universe. Allow this feeling of deep and easy peace to flow down from your shoulders, into your arms, and all the way to the tips of your fingers. Your arms and your hands have been working for you all day, carrying and holding and doing. Now is their time to simply be. Allow them to feel heavy, warm, and completely still. Let go of the need to do anything at all. Now, bring your awareness to your neck and your shoulders, another place where we carry the burdens of the day. As you exhale, imagine the weight on your shoulders gently dissolving. Feel the muscles in your neck becoming soft and long. Let go of all the weight you have been carrying. And finally, bring your awareness to your head and to your face. Gently release any tension you may be holding in your jaw. Allow your tongue to rest gently in your mouth. Soften the tiny muscles around your eyes, and smooth out the space on your forehead, between your eyebrows. Your entire body is now in a state of deep and quiet and profound rest. It is your anchor, holding you safely and peacefully in this present moment, and all that is left to do is to rest here, and to float on the gentle, silent tide of your own breathing. You have now arrived at a place of deep and profound stillness. The great cosmic journey is complete. The story has been told, and the mind has been quieted by the beautiful and gentle wonders of the universe. Your body is now in a state of perfect and quiet readiness for sleep. The day is behind you, and the great, silent, and restorative ocean of the night is before you. There is nothing left to do now, and nowhere else to be. The only journey that remains is the one into the gentle and healing quiet of your own rest. You do not need to seek it. You do not need to force it. You simply need to allow it to arrive in its own perfect time, like a gentle and a welcome tide. And so you can let go now. Let go of the story, let go of the day, and give yourself permission to drift, floating now on a quiet and comfortable sea of peace, drifting gently, deeper and deeper into the quiet, into the calm, into the wonderful and restorative silence of sleep. Rest now. Just rest. The journey continues, always calmly, always at the pace of the universe.